Hello everyone. We will now begin our lecture on chapter 5.3, which is the third section in chapter 5. Now chapter 5 is on number theory. The different sections talks about the different types of numbers as well as patterns, sequences and so on. However, for our course, we will only cover the third section, which is on rational numbers. Now, the word rational comes from the word ratio, and ratio of two numbers is represented as a fraction. All right, so ratio and fractions are often used interchangeably. All right, and fractions, as you know, they have a numerator and a denominator, right? So fractions can be written, and I'm just going to use general variables here, P over Q. All right, so in any fraction, there's a numerator as well as a denominator. Now, sometimes their denominator may not be visible, and when that happens, when the denominator is not visible, that means it is a 1. The denominator has a value of 1. So we will go into the details of that. We will talk more about rational numbers and how to perform operations with rational numbers. All right, this was just meant to be an introduction on what we are going to discuss through this section. Let's quickly go over some of the topics that we will cover in this section. First of all, we will learn to reduce fractions to its lowest terms, and then we will learn how to convert mixed numbers to improper fractions and vice versa. For that, we have to first understand what mixed numbers are and what improper fractions are, and then we will learn how to convert one to the other and vice versa. Then we'll also talk about expressing rational numbers as terminating or repeating decimal numbers. Additionally, we will know how to convert decimal numbers to fractions. So a decimal number, to convert them to fractions. And then finally, we'll talk about the different operations on fractions: multiplication, division, addition, and subtraction of fractions. Now let's first look into a definition of rational numbers. So the set of rational numbers denoted by the uppercase Q is the set of all numbers of the form P divided by Q, where P and Q are integers and Q, which is in the denominator, is not a 0. Q can be a 1. However, it cannot be a 0 because division by 0 is undefined, right? So that is the definition of rational numbers. Let's look at some examples of rational numbers. So if the first number we have here is 1 over 3. So in any rational number, rational numbers essentially are fractions. Remember, the numerator is represented by P and the denominator is represented by Q, and the numerator and denominators must be integer values. So in this case we have 1 and 3, so 1 divided by 3, which makes it a valid rational number. We have 3 divided by 4. We have negative 7 over 8 minus 7 over 8. So that means rational numbers can be negative. Rational numbers can be positive as well. Now this number here is 1 and then 2/3. So 1 is an integer value. It's a whole number. And then next to it we have a fraction which is 2/3. And that this makes this entire value 1/2 1 and 2/3 mixed fraction. That means it has an integer part to it as well as a fraction part to it, and it's called a mixed number. All right, it's called a mixed number. And then we have 2, which looks like an integer, which is an integer value. However, it is also a rational number. It is also a rational number. We don't see the denominator visible. However, when you don't have a denominator visible, that means the denominator is a 1. All right, 2/1. And then 0 is also a rational number. It's like 0/1. Remember, Q can be a 1 or any other value. However, it cannot be a 0. And then 15/7. Now 15/7, we normally in all these examples, we have the numerators less than the denominator, except for these numbers where the denominator is a 1. However, when we have a visible denominator and we see that the numerator is larger than the denominator, it's called an improper fraction. An improper fraction. And we'll look more into examples of mixed and improper fractions. All right. So here are some of the examples that we have seen related to the definition of a rational number. Now let's look into fractions in particular. Now, even though we use the terms rational number and fractions interchangeably, there is a slight difference between a fraction and a rational number. A rational number can be an integer. That means an integer value, a whole number, can be a rational number. However, a whole number is not a fraction. So in the previous slide, we saw an example where they had the number 2 and they said that that's a rational number. Likewise, the number 52 would also be considered a rational number. It is also an integer. So integers can be rational numbers. Integers are rational numbers. However, these numbers 2 and 52 are not fractions. Why? Because their denominator is a 1. All right. In order for a number to be a fraction, the denominator has to be something other than a 1, and definitely no rational number can have a denominator of 0. That goes without saying. However, for a fraction, or in order for a number to be a fraction, the denominator needs to be a value which is other than a 1. All right, so fractions are numbers such as 1/3, 2/9, and 9/53. The number on top of this fraction line, which also represents division. 1/3 is the same as saying 1 divided by 3. 2/9 is the same as saying 2 divided by 9. Correct? Same with 9/53. The number on top is known as the numerator, the number that's above the fraction line, that is. And then the denominator is the number below the fraction line. And in order for it to be a fraction, the denominator must be a value which is greater than 1 or something other than 1, right? Now, one operation that we must know to perform on fractions is to reduce it to its lowest terms. What does reducing a fraction to its lowest terms mean? It means that we write the fraction such that the numerator and denominator have no other common factors except the number 1. All right, that means the numerator and the denominator can only be divided by 1 and no other value. For example, let's look at this fraction here, 2 over 3. Can you think of a number which will divide both 2 as well as a 3? A number which is something other than 1. All right. The only number that is common, and that will divide both 2 and 3 is a 1 and none other. All right. So when that happens, then this fraction is already reduced to its lowest terms. However, if we take another fraction, 6 over 15. All right. Now 6 over 15, let's see what numbers will divide both 6 as well as 15. So 1 we know will divide both 6 and 15, but we are not just looking at 1. Let's see if any other number will divide both 6 and 15. 2 will divide 6, but 2 will not divide 15. All right, so 15 is not divisible by 2. 6 is divisible by 2, correct? So let's move on to the next number, 3. All right, 6 can be divided by 3, right? And 15 can also be divided by 3. All right, so there is a common divisor, common factor that will divide both 6 as well as 15. And in this case, that is the number 3. All right, so 6 divided by 3 and 15 divided by 3 gives us 2 over 5. Now let's look at 2 over 5. Is there any number, any value which will divide both 2 and 5 other than 1, right? So there's no other number except 1 that is common to 2 and 5, and that will divide the numerator as well as the denominator. There's no common divisor. Therefore, now we have reduced 6 over 15 to its lowest terms, and that's 2 over 5. All right, so this is how we are going to learn how to reduce fractions. In the next slides, we will go through some examples of this. All right, so this was just explaining what we mean by reducing a fraction to its lowest terms. Now let's go through this example on reducing a fraction to its lowest terms. The fraction they've given to us is 54 over 90, and we have to reduce it or write it in its lowest terms, meaning that the numerator and denominator cannot be divisible by any other value except a 1. Currently, we see that 54 and 90 are both divisible by at least 2. However, to be able to write it in its lowest terms, it's not the smallest value that will divide both the numerators and the denominator, but it should be the highest value, and that is called the greatest common divisor. All right, greatest common divisor, but we have to know how to find the greatest common divisor. So let me teach you a way of doing that. Take your two values, 54 and 90. All right, so we write these two values, and then what number, think of the smallest number that will divide both 54 and 90. Both are even numbers, so we know that they will be divisible by 2 at least, correct? So I'm going to write the 2 here and divide 54 by 2. All right, 54 divided by 2 is 27, and 90 divided by 2 is 45. 45, correct? Now think, what number will divide both 27 and 45? Is there a number that divides both 27 and 45? So the number 3 divides 27. 27 divided by 3 is a 9. All right. And 45 divided by 3 is a 15. Correct? So in the next step is think if there's any other number that will divide both 9 and 15. Obviously, that's 3 again. 9 divided by 3 is 3. 15 divided by 3 is a 5. So I'm going to divide 9 and 15 by 3 and write the quotients here. 9 divided by 3 is a 3 and 15 divided by 3 is a 5. And then 3 and 5 cannot be divided by any value except maybe a 1, correct? So at this point we can stop, all right? We stop, and what we do is we multiply all these values on the extreme right hand side, all right, and the on the extreme left hand margin is what I mean to say. All right, so 2 multiplied by 3 multiplied by 3 multiplied by 1, correct? So 2 times, we can ignore the 1 because it will not make any difference to the product. So 2 times 3 times 3 is how much? 2 times 3 is 6, 6 times 3 is 18, and that is called the GCD, also called the GCF, sometimes F for factor. So greatest common divisor or the greatest common factor. So 18 is the largest number that is common to both 54 and 90, and by which both these numbers are divisible. So if you do 54, all right, 54 divided by 18 and 90 divided by 18, you will get 3 over 5. All right, so 3 divided by 5. And now at this point, this fraction, 54 over 90, has been reduced to its lowest terms. All right, so this is how you find the greatest common divisor. And then, you divide the numerator and denominator by the greatest common divisor and write the answer in its lowest term. So let's see how they've worked out the problem over here, how the book has worked out the problem. So here's the solution. The GCD of 54 and 90 is 18. Now they didn't show us how to find the GCD, but I've shown you here. You can follow the same process to find the GCD, and once you have your GCD, you divide the numerator and the denominator by 18 in this case, which gives us 3 over 5. All right, so this is how we go about reducing a fraction to its lowest terms. Now another way, if you don't want to find the GCD at once, then you have to keep dividing it by the numbers, all right, by the least common multiples, and you have to keep dividing until you get to a point where you end up with the lowest, or until you get the fraction in its lowest terms is what I mean to say. All right, so what we can do here, let me just show you what I'm trying to explain here. So if you can start with 54 divided by 90 and divide first by 2, right? Divide by 2, and that will give us 27 over 45. And then 27 and 45 are both divisible by 3. So divide both of them by 3, you'll end up with 9 over 15, and then again divide 9 and 15 by 3, and you will get 3 over 5. And that's, at this point you can stop because 3 and 5 don't have a common divisor except 1. All right, so this is another way you can go about reducing a fraction to its lowest terms, or you can find the greatest common divisor first and then divide the values in the numerator and denominator by it. All right. So now that we have gone through the process of reducing a fraction to its lowest terms, we will talk about what's called a mixed number. Now, a mixed number consists of an integer value as well as a fraction. So in this number 2 3/4, there are both kinds of values. An integer value, which is 2, and as you can tell, 3/4 is a fraction, 3/4 is a fraction. So this a complete number here, 2 3/4, is a mixed number because it contains not only a fraction but also an integer. So what we are going to learn is how to change this mixed number to a fraction without the integer part. All right. And when we do that, it will be called an improper fraction, right? So it says here 2 3/4 is read as 2 3/4 or 2 3/4, and it means 2 plus 3/4. All right. That's what a mixed number is about. So what is an improper fraction? Now, in an improper fraction, what happens is the numerator, all right, the numerator is always greater than the denominator, all right? So improper fractions are created or are derived from mixed numbers, which has an integer part, and whenever a mixed number is converted to a pure fraction, it is an improper fraction because the numerator will always end up being a value greater than the denominator. All right, so let's look at how they'd have defined improper fractions. It says here, rational numbers greater than 1 or less than -1 that are not integers may be written as mixed numbers or as improper fractions. All right, so mixed numbers have an integer part as well as a fractional part, right? And when we convert that to a pure fraction, when we get rid of the integer part of it and convert it to a pure fraction, we will always end up with an improper fraction, and we will see that the numerator in that fraction is greater than the value in the denominator. So an improper fraction is a fraction whose numerator is greater than its denominator. An example of an improper fraction is 8/5. All right, so we will learn not only how to convert from a mixed number to an improper fraction, but we'll also learn how to convert an improper fraction back to a mixed number. All right. Now, in order to explain how to convert a mixed number to an improper fraction, I think it's best to start with some examples and show you the process, and then we can go on to the next couple of slides where they first explain the process and then go through the examples. All right, so it'll be easier for me to explain as well as easier for you to understand if I start with an example and show you exactly what I'm trying to do in order to do this conversion. All right, so let's take this number, this mixed number here, which is 2 3/4. All right, 2 3/4. I want to convert that to a fraction. That means get rid of the 2 and write it as a fraction, as a complete fraction, by eliminating the integer part, but we cannot change the value of this number. All right, so the way to go about it is in your result, in your answer for the improper fraction, just write the denominator the same as you have in your mixed number. All right, so that doesn't change. In the denominator, you will have a 4, which is the same as the denominator in the mixed number. we have to figure out what to put in the numerator. So to find the value, to calculate the value in the numerator, all you do is you multiply the denominator with the integer. So you multiply 4 and 2 in this case, and then to that product you add the 3 or add the value in the numerator. So what I'm going to do is 4 times 2 is 8, and 8 plus 3 is 11, and that's the value I'm going to put in the numerator. All right, so 2 3/4 when converted to an improper fraction gives us 11/4. Right? Let's take another example. How about 3 and 2/5? 2/5. 3 and 2/5. And maybe I should write the 3 somewhere in between the 2/5, so somewhere here. All right, so it doesn't look like 32. Again, same process. For the denominator of the improper fraction, we are going to come up with, use the same denominator value, which is a 5. But to come up with the value in the numerator, multiply 5 with 3. All right, we multiply the denominator with the integer value, that's a multiplication, and then add 2 or add the value in the numerator to the product. So 5 times 3 is 15, 15 plus 2 is 17, and that's what goes in the box in the numerator. So 3 and 2/5 when converted to an improper fraction becomes 17/5. All right, so this is how we are converting a mixed number to an improper fraction. Now let's go to the next slide where they explain, or where they write out the steps we performed. So here are the steps written out to convert a positive mixed number to an improper fraction. So let's see if we followed the same process that they have written out for us this time. So we worked with 3 and 2/5, right? That was one of the examples we worked previously, 3 and 2/5. So it says here, multiply the denominator of the fraction in the mixed number by the integer preceding it. So it's 5 times 3. That's what they are asking us to do. So 5 times 3 is 15, and then in the next step, add the product obtained in step 1. So this was 15, 5 times 3 that we obtained after multiplying the denominator by the integer value. And then add the product obtained in step 1. So now we have to add the product with the numerator value. So add the product obtained in step 1 to the numerator of the fraction. So 15 plus 2, 17. So this sum is the numerator of the improper fraction we are seeking. So this is going to be the 5 times 3, 15 plus 2 is 17. That's going to be the numerator. And what about the denominator? We said the denominator will be the same as the denominator in the mixed fraction. So the denominator of the improper fraction we are seeking is the same as the denominator of the fraction in the mixed number. So in that case, it's a 5. So just write that value underneath as the denominator of the improper fraction. All right, so that's how it's the same process that we followed, except that in the previous slide when we were demonstrating the process, we first wrote out the denominator and then we found the value of the numerator by multiplying the denominator by the integer and then adding the numerator to the product, right? Now some more examples of converting mixed numbers to improper fractions. They have the mixed number here 2 and 3/5. So they put the denominator the same value as was in the mixed number. So 5 goes for the denominator of the improper fraction, and to calculate the value in the numerator they did 5 multiplied by 2. So the denominator multiplied by the integer part and then added 3 to the product. Remember, by the order of operations, we must multiply first. Multiplication comes before addition. So 5 times 2 plus 3 should give us 13 over 5. So let's see the final answer. 5 times 2 is 10, plus 3 divided by 5 gives us 13 over 5. All right. So there's another example following this. So let's see what the next number is. So the mixed number is 4 and 7/8. So in the next step, we should see the same denominator as in the mixed number. So the 8 of 7/8 becomes the denominator of the improper fraction that we're going to come up with. And for the numerator, it's 8 times 4. Again, the denominator times the integer part plus 7. So 8 times 4 plus 7 should give us a value of 32 plus 7. Again, multiplication before addition. Don't forget that. You should not do 4 plus 7 multiplied by 8. That would give a completely different and wrong answer. All right, so 8 times 4 is 32 plus 7 divided by 8 for a value of 39 over 8. So in all these examples, we see the value of the numerator is greater than the value in the denominator, thus making it an improper fraction, right? Now let's learn how to convert improper fractions to mixed numbers. Okay, so again, I'm going to start with a demonstration with examples, and then in the next slide we are going to read through the process of the conversion. All right, so let's pick an example here, an improper number which is 8 over 3. All right, so this is an improper fraction. How can I tell that? Because the numerator, the value of the numerator is greater than the value of the denominator. When that happens, then it's regarded as an improper fraction. So we have to convert this to a mixed number. That means there'll be an integer part as well as a fractional part when we do the conversion. So the process of doing that is take your numerator and divide it by the denominator. All right, so I'm going to do that on the side. I'm going to take 8 and divide it by 3. All right, so divide your numerator by the denominator. So 2 times 3 is 6, correct? And then do the subtraction. 8 minus 6 is 2. And you stop there with the division. All right, now we can write it as a mixed number. So the number, the quotient, the value of the quotient on top here, this is the quotient, is your integer part of the mixed number. All right, so I'm going to write that as 2. And then the fractional part is formed by using the remainder over the divisor. All right, so 2 over 3. So let's write that. So 2 and 2/3 is the answer. 2 and 2 over 3. So we've converted the improper fraction to a mixed value. Let's take another example, a larger number maybe. I'll use 159 over 5. All right, so this is again an improper fraction. The numerator is greater than the denominator. We start the division process on the side. So 159 divided by 5. So 5 times 3 is 15. So 15 subtract, and then this is 0, bring down the 9. And then 5 goes into 9 once, so 31. You write the 1 on top, making the quotient 31, and write the 5 below, and the remainder is 4. So once you get a remainder, you can just you can stop the division and write it as a mixed number. All right, so now this 31 is going to be the integer part of the mixed number. So I'm going to write 31. This quotient value here from the division becomes the integer part of the mixed number, and the fractional part is the remainder over the divisor, so 4/5. So let's write that. It's 31 and 4/5. And that's how we convert an improper fraction to a mixed number. So in the next slide, we're going to read through the process, all right, and then we'll look at some examples that was provided by the book, all right. Let's now go through the process of converting a positive improper fraction to a mixed number and see if it's similar or is the same as what we used when doing the conversion. All right. So first step, it says divide the numerator by the denominator, identify the quotient and the remainder. And then in step 2, the quotient obtained in step 1 is the integer part of the mixed number. The remainder is the numerator of the fraction in the mixed number, and the denominator is the fraction of the mixed number. It will be the same as the denominator in the original fraction. So in other words, the denominator of the mixed fraction will be the divisor. All right. So let's go on to the next set of examples that the book had provided through these slides and go over it. All right. So here's an example of converting the improper fraction to a mixed number. The improper fraction provided to us is 8/5. So the first step is to perform a division, that is divide the numerator by the denominator. All right, and that's what they have done here. They have shown the process of division. 8 divided by 5. 5 times 1 is a 5. So we write the 1 on top, 5 below the 8. 8 minus 5, we do perform a subtraction. Yeah, 8 minus 5 is 3, and once we get the remainder, we can stop the process of division and write it as a mixed number. So your quotient 1 will become the integer part of the mixed number, and the fractional part will be the remainder over the divisor. So it's 3/5. So in the next slide, they have written it out as a mixed number. I've already done the work here, but let's go and see if they have the same answer as us. So here we go. We have the final answer written out as a mixed number from the results of the division. So the quotient from the division was a 1, and that becomes the integer part of the mixed number. And for the fractional part, the remainder, which was a 3, becomes the numerator of the fractional part, and the denominator of the fractional part is the divisor. And this denominator of the mixed number is going to be the same as the denominator in the in the improper fraction. All right. Another example here to convert an improper fraction to a mixed number. We have a 3-digit numerator here, which is a larger number. But how do we convert it to a mixed number? Again, we start with the process of division. So let's look at the solution. They have 225, and they're dividing that by the denominator, which is the divisor. And 8 times 2 is 16. So they have the 16 here. They subtract. This is a subtraction here. So 22 minus 16 is 6. Bring down the 5. And then 8 times 8 is 64. And they have a remainder of 1. So stop here. And we have to now put it in mixed put together the results of the division as a mixed number. So how do we go about doing that? We use the quotient as the integer part. So 28, the quotient is the integer part of the mixed number, and then the remainder here becomes the numerator, and the divisor or the denominator of the improper fraction becomes the denominator of the fractional part of the mixed number. All right, so let's go on to the next slide to see if they have put it together with the same answer, right? So here's the final answer to convert 225 over 8 to a mixed number. So after we did the division in the previous slide, the quotient was 28. That becomes the integer part of the mixed number. The remainder becomes the numerator. Remainder was 1. It becomes the numerator of the fractional part. And the divisor becomes the denominator of the fractional part. And the divisor or the denominator of the fractional part is the same as the denominator of the improper fraction. Now let's discuss another topic related to rational numbers, and that's called terminating and repeating decimal numbers. So we can express rational numbers in the form of decimal numbers. So fractions can be changed to decimal numbers. So here it says every rational number when expressed as a decimal number will be either a terminating or a repeating decimal number. So I'm going to give you an example of what a terminating decimal number looks like versus what a repeating decimal number looks like. Now, a terminating decimal will have its decimal values, the decimal portion of the number, end at a certain point in time. All right, whereas the repeating decimal number will never end. All right, you can keep on performing the division and you will never end up with a 0 as the remainder. All right, so let me give you an example to make it more clear for you. So first, an example of terminating decimal number. Let's take this fraction here, 9 divided by 2. All right, so this is an improper fraction, but this time we want to convert this to a decimal value. All right, we are not trying to convert it to a mixed number. It's slightly different. We are going to change it to a decimal value, but the process is somewhat the same. All right, you have to perform division. So I'm going to take the numerator divided by 2 in order to convert it to a decimal value. So 9 divided by 2. I'm working this on the side. 2 times 4 is 8. So I'm going to write the 8 below the 9. And then we have a remainder of 1. And then there are no other digits next to 9. But we can add a decimal point next to the 4, to the right of 4. And we can add a 0 next to the 1 in the remainder. All right. And then we perform the division again. 2 times 5 is 10. We do the subtraction and we get a remainder of 0. So 9 divided by 2 in decimal is 4.5. And when we get a remainder of 0, that means the decimal terminates there. All right, so 4.5 or 4.50. If you want to show more decimal places, then it can be 4.500 or 4.5000. It'll only be zeros. All right, so this is an example of a terminating decimal value. So we convert 9 over 2 into decimal. We get a terminating decimal number, which is 4.5. All right. To give you an example of the repeating decimal number, let's take the fraction 4 over 3. All right. So 4 divided by 3, let's do the division to see what decimal value we get. So over here on the side, let's do the division. 4 divided by 3, and I'm going to move this up a little bit because I might need more space. 4 divided by 3, right? So 3 times 1 is 3. So I write the 3 below the 4, and there's a 1, all right? A remainder. I have to put a decimal point next to the 1 in the quotient, and then I can put a 0 next to the 1 in the remainder, right? Now, 3 times 3 is 9, correct? So I put the 9 below the 10, and 10 minus 9 is a 1. And now I can, once you put the decimal place only once, all right? After that, you can keep adding zeros to the remainder. So 0 next to the 1. Again, 3 times 3 is 9, all right? 10 minus 9 is a 1. Again, a 0 next to the 1, and then a 9. And if you can keep going like this, let me use a different color here, 1, 0, and you can keep going, and you will end up getting 1.33333, however many times you keep performing going on with this division. All right, so this is an example of a repeating decimal. So it's 4 divided by 3 in decimal can be written as 1.333. All right, you can keep going on and on and on, and because it is a non-terminating decimal, you just put a bar over the last 3, and which indicates that this is a non-terminating repeating decimal number. All right, so this should clarify the difference between a terminating decimal and a repeating decimal number, and we will go through some examples of this provided by the book. All right. So here are some examples of terminating or repeating decimals. The first set are examples of terminating decimal numbers, and they are 0.5, 0.75, and 4.65. So that means in 0.5 there are no decimal values after the 5. Same for 0.75. There's no decimal values that come after 5. And then same for 4.65. Right? So the next set are examples. Next set is examples of repeating decimal numbers like 0.333 that we worked out before, which may be written as 0.3 with a bar on top. Then that bar tells us that the 3 keeps repeating. And then 0.2323, when we write it as in non-terminating notation or repeating decimal, the bar has to be over 23 because that's the pattern that's repeated. So 0.232323, that's the pattern that will get repeated. So the bar should cover 2 as well as 3, should go over both these numbers. And 8.13456, 456, 456. So in this case, you have to put the bar over the repeating pattern. So 456, all 3 digits have to have the bar over them to suggest it's a repeating decimal number. Now here's a set of examples where we convert a fraction, a rational number, into a terminating decimal number. So it says here, show that the following rational numbers can be expressed as terminating decimal numbers. Now the way you convert a fraction to a terminating decimal number is by dividing the numerator with by the denominator. However, to prove that it's a terminating decimal number, the division at some point is going to result in a remainder of 0. All right. So if you end up at some point in the division process with a remainder of 0, that means it's a terminating decimal number. So what I'm going to do here is I'm going to perform the division and then see whether it is terminating or not. So it's 4 divided by 5. So I'm going to work the division on the side. So I have 4 and I divide it by 5. Now 4 is less than 5. We have to have the dividend greater than the divisor. Divisor here is 5 and the dividend is 4. So we need to make this number somehow greater than the divisor 5. So we need a 0 next to the 4. Now in order to make or bring a 0 next to the 4, to write a 0 next to the 4, we need a decimal point. Now, so we can, if we put a decimal point here, then we can write a 0 next to the 4. Now, it's always a good practice to, when a number starts with a decimal point, it's always good practice to put a 0 to the left of the decimal point. All right, because sometimes the decimal point may not be visible, especially if you're writing with pencil or in a hurry. The decimal point so it's always a good practice to have a 0 to the left of the decimal point if the value starts with the decimal point. All right. However, if you do not write the 0, it's not wrong. All right, but it's just good practice. So 0 point, and then we can perform the division now. 5 goes into 48 times. So I write the 40 below, subtract, and we end up with the remainder of 0. So now this decimal point 0.8 is a terminating decimal number because we ended up with a 0 for the remainder. So 4/5 can be written as 0.8. All right. So let's see if they got the same answer over here. All right, 0.8. Now they haven't shown the division. I have demonstrated the division process over here. They have just given us the answer. So it is 0.8, and the way they got it is by performing this division and then stopping once you end up with a 0 as the remainder. Let's see if there are any other examples. B is minus 21 over 25. So again, we have to perform the division. 21 divided by 25. However, for the time being, I'll just ignore the minus. When you're performing the division, you can ignore the minus. But at the end, when we write the answer, there should be a minus. All right. So 21, again, I'm going to work on the side. 21 divided by 25. Again, 21 is less than 21. Sorry. 21 is less than 25, correct? So I need a 0. I have to somehow make this dividend larger than the divisor. So I needed to put a decimal point in the quotient. So again, I'm going to start with a 0, and next to the 0, I put the decimal point, and then I can add a 0 to 21, or put a 0 next to 21 to make it 210. And now I can go ahead and perform the division. So 25 times 8 is 200, correct? So 200, subtract, and then we have a remainder of 10. So now I put a 0 next to the 10. Now we've already, once we have already put a decimal point, we do not need to put another decimal point to bring a 0, all right, next to the, to write a 0 next to the remainder. So again, let's continue with the division. 25 times 4 is 100. So I'm going to write the 4 next to the 8, and then 100 here minus, and now we have a remainder of 0. So the final answer is, however, again, do not forget the negative sign, negative 0.84. And yes, this is a terminating decimal number because after 2 iterations, we ended up with a remainder of 0. All right, let's see if there are any other examples. Oh, okay, they show the answer here. Negative 0.84 is the same as what we got after we performed the division. So what is the next one? So 97 divided by 40. So let's perform this division now. So 97 divided by 40. So 97 is greater than 40. So we do not start with a decimal now. 40 times 2 is 80. All right. So 80 minus. So we have 170. All right. So there's no 0, right, next to the 97. So to write this 0 here, we need to put a decimal next to the 2. All right. So now we continue with the process of division. 40 times 4 is 160. All right, then subtract. 7 minus 6, 1, 0. And somehow this point got erased, the decimal point. And then I write another 0. And 40 times, again, 40 times 2 is 80. Right? So until we end up with a remainder of 0, we have to continue with the division process. All right, if it's a terminating number, or to find out if it is a terminating number or not. So 20, again now 0. So 40 times 5 is 200. And now we have a 0 at last for the remainder. All right, so 97 divided by 40 should give us a result of 2.425. So it terminates after 3 decimal places. So 2.425. Let's see what answer they come up with. 2.425 as well. All right. So 2.425. It's gotten hidden. Let me just erase this part. 2.425, which is the same as the answer we came up with after we performed the division process. Now the next set of examples is to show that rational numbers can be expressed as repeating decimal numbers, non-terminating decimal numbers. So we saw that for in terminating decimal numbers, after we perform the division, at some point in the division process, we will end up with a remainder of 0. And we can stop the division process there. For repeating decimal numbers, we keep on dividing. We keep going through the division process, but we never end up with a remainder of 0. And often the remainder in each iteration will end up being the same. There'll be a pattern to the quotient. All right. So the first example is 2/3. So let's go through the division process and see whether this is a terminating decimal or a non-terminating decimal. So 2 divided by 3, all right? So again, 2 is less than 3, right? 2 is the dividend is less than the divisor, which is a 3. So we need to start with a decimal point. And like I said, as good practice, I just put a 0 to the left hand side of a decimal point when a decimal value starts with a point. All right, decimal point. So 0 point, and once I have the decimal point, I can just put a 0 next to the 2, and then I start the division process. All right, so 3 times 6 is 18. That's the closest we can get to 20 without going over. So 6, and then we write the 18, and then subtract. we end up with the 2 again as the remainder. And then now I can put another 0 and continue with the division process. Again, 6 threes are 18 minus 2, 0. Again, 6 threes are 18. So we see that the remainder is getting repeated in each iteration, and so is the 6 in the quotient. So and if you keep continuing, you will end up getting 6, 6, 6, 6, and a remainder of 2, 2, 2, as long as you, or as far as you go with the division. All right, so we can stop. We have to stop at some point, and we can write the quotient or the answer as 0.666, or we just write it as 0.6 with a bar over the 6, all right, which says that this is a repeating or non-terminating decimal number. Okay, so let's look at the next example. The next one says, just a second, let me pull that up. It's 14 over 99. So again, continue or start with the division process. 14. All right, let's do it here. 14 divided by 99. 0.1401 is 99. So that's 61. Sorry, 50. 59. All right, 59. And then we put a 0. 99 times 4, or is it 99 times 5, right? 99 times 6, 99 times 6. So 9 6 are 54. It's 54 plus 550, that goes over 1.5, which should probably be a better value. 9 5s are 45, 9 5s are 45, and 4 49. So that's 5. Then 9 take away 10, take away 9. 85. Okay, so I'm going to erase this and do this all over again. All right, so 14 divided by 99, 0.0. So ones are 99, 151, 0. 9 4s are 36, 3, 7, 30, 39. And then we have a 4. Then 1, 0, 1, 140, right? So we have a 1, 99, 5, 1, 0, 4, 396, and so on. Okay, and then we have 1 5 over 36. So first we have to convert this to an improper fraction. 36 times 1 plus 5, 41 divided by 36. Now, the next few slides are about converting decimal numbers to fractions, and I think I will put up a separate video explaining the process of converting decimal numbers to fractions. But we can convert both terminating We can convert terminating as well as repeating decimal numbers into a quotient of integers into fraction form. All right, but uh, like I said, I will put up a separate explanation of that. However, as part of this presentation, we will talk a little bit about the positional values of the decimal part of a number. So the explanation of the procedure will refer to the positional values, the place values to the right of the decimal point. So the decimals start from are placed to the right of the decimal point, isn't it? So we'll go on to the next slide and talk about the positional values. Now here's a picture, a diagram of how a decimal number looks like. So we have the decimal point and all the everything to the right of the decimal point represents the fractional part or the decimal part of the number. All right. So to the left of the decimal are the place values are the units position, then the tens position, then the hundreds position, then the 1000 position, and so on. To the right of the decimal point, it's tenths position, THS. So tenths position means 1 divided by 10. Then the second decimal place is the hundredths position, which means 1 divided by 100. Then 1000 is 1 divided by 1000. All right, so if you recall when we were talking about the place value in the decimal system, then for any decimal number, an integer number, let's say 5, 7, 6, all right, let's look at this 3-digit number. The 6 was called the units place, or it had a positional value of 10 to the power 0. 7 had a positional value or the place value of 10 raised to the power 1, and then 5 was in the positional value uh, of 10 squared, 10 to the power 2. All right, in the decimal part of the number, it's the other way around. It starts with 10 to the power 1, but it's 1 divided by 10 to the power 1, 1 divided by 10 to the power 2 for the hundredths position, then 1 divided by 10 to the power 3 or 1000ths position, 10,000ths position, 100,000s, millions, and so on. All right, so we have to remember the positional values of the decimal part now, just as we know the positional value of the digits to the left of the decimal point, right? Now what I'm going to do is I'm going to skip this slide here where there's an example of converting a repeating decimal number to a fraction. I'm going to skip this and take it on in a separate video because it's difficult to explain it with just one slide and there's not much place available to write it out and explain. All right, so again, like I said before, that this part of the section I will treat in a separate video. All right, so we'll move on to the next slide, which is on performing arithmetic operations with fractions. We will now talk about the arithmetic operations that can be performed on fractions. The 4 arithmetic operations essentially are addition, subtraction, multiplication, and division. And we are going to start off by talking first about multiplication, right? So when we multiply two fractions, all we do is multiply the numerators and multiply the denominators, and the product of the multiplication would create another fraction. So let's say we have this fraction 3 over 7, all right, and then another fraction uh, that we multiply 3/7 with, that would be, let's pick 2 over 5. All right, so to perform this multiplication, all we do is multiply 3 and 2 to get a 6 in the numerator. So we multiply both the numerators, and then 7 times 5 is 35. So we end up with another fraction, which is a product of these two fractions, 3/7 and 2/5. We get an answer of 6 over 35. All right, so let's see what they say here. The product of two fractions is found by multiplying the numerators, and that's what we did here, together, and multiplying the denominators together. All right, as simple as that. So if in general terms, one fraction is a divided by b, and the other fraction is c over d, and we want to multiply them, then just multiply a and c together to get ac, and b and d, the two denominators, are multiplied to get bd. However, make sure that the denominators cannot have a 0, because division by 0 means you end up with an undefined value. All right, so as long as the denominators are not 0, in this case b and d are not 0, we can just go ahead and multiply the numbers in the numerator and the numbers in the denominator to come up with the answer of multiplication. So here are a few examples that we'll work on. We have 3/5 for one fraction and 7/8 for one fraction, and we will need to multiply. So we know that all we do is multiply the numerators. In this case, 3 times 7 is 21, and 5 times 8 is 40. So our answer should be 21 over 40. All right. The next one, let's look at another example. Just a second, let me pull it up here. All right, so 21 over 40 is what we get. Let me erase this. The next one is -2 over 3. All right, so one of the fractions, well, in this case, both fractions are negative, -2/3 and -4/9, correct? So here, because we have a negative sign, we have to multiply the negatives, correct? So multiplying two negatives gives us a positive value. So let's do that. -2 times, and let's work on the side because otherwise it's going to clobber it. So -2 times -4 is a positive 8. All right, so I'm going to write 8 for the numerator, and 3 times 9 is 27, so the answer should be 8 over 27. All right, so you have to be careful when there are signs on the fractions. You can either put the sign in the numerator or in the denominator, won't make a difference. It'll still end up with whatever sign results from the multiplication. All right, so in this case they have put the sign to the numerator, so -2 times -4 is a positive 8, and the denominators are left as positive, so 3 times 9 is 27. All right, so let's see what answer they have come up with. So -2 times -4 and 3 times 9 results in 8 over 27 is what we got as well. All right, then there's a third example. Let's pull that up. It's mixed fractions, mixed numbers, right? So 1 and 7/8 and 2 and 1/4. So in this case, we would first convert the mixed number to an improper fraction. How do we do that? It's 8 times 1. So it's denominator times the integer value plus the numerator. 8 times 1 plus 7 should give us 8 plus 7, 15 over 8. The denominator of the improper fraction is the same as the denominator in the fractional part of the mixed number. So we will end up for the first fraction or the first number, it's going to be 15 over 8. And we do the same thing with the other number, 2 and 1/4. So 4 times 2 plus 1, correct? Let me write that. 4 times 2 and then plus 1. So 4 times 2, 8 plus 1, 9. So we end up with 9 over 4. And then just multiply it out. So we'll get 15 times 9. 9 fives are 45, 5, 9 ones are 9 plus 4 gives us a 13. 135 over 8 times 4 is 32. All right, so let's see what they got and how they worked this out. Here, I may have to erase my work to see what they got. So they got 15 over 8 was the same as what we got. 8 times 1 plus 7, 15 over 8. And 4 times 2 plus 1, 9 over 4, right? And then they multiplied the numerators and the denominators to come up with a value of 135 over 32, which is the same answer as what we came up with, right? Now, before we go into learning about the next operation with fractions, which is division, we have to understand what the reciprocal of a number is. Now, the reciprocal of a number, of any number, is 1 divided by that number. So if we have 2 for our number, the reciprocal of 2 is 1 divided by this number 2. So reciprocal of 2 is a 1/2. Let's look at a fraction here. Maybe 2 over 5. This is a fraction, correct? 2 over 5. If I want to find the reciprocal of that, we can do 1 divided by, all right, it's the same as doing 1 divided by 2/5. And the result will be, what we will end up with is the numerator of the original fraction. So the numerator of the original fraction will go to the denominator and the denominator will go to the numerator. So essentially we will end up flipping the numerator and the denominator. So we are going to get 5 over 2. So you will get this result when you do 1 divided by the fraction or 1 divided by whatever number, whether it's integer or fraction. You will end up with switching, inverting the numerator and the denominator. So the same thing happened here when we worked with 2. 2 is written as 2 over 1, right? An integer value, any integer value can be expressed in fraction form by putting a 1 in the denominator, 2 over 1. So when we found its reciprocal by dividing 1 by 2, what did we end up with? The denominator of the original fraction became the numerator of the in the reciprocal, and the numerator in the original value, original number, became the denominator in the reciprocal. All right, so the reciprocal of any number is 1 divided by that number. And another thing about reciprocals is the product of a number and its reciprocal must equal 1. So product implies multiplication. So if you multiply the reciprocal of each other, then you will end up with an answer of 1. So 2 over 1 multiplied by, so let me try to multiply, these are the reciprocals. What do we end up with? 2 divided by 2, right? We end up with, and let me pull up another color here. All right, we end up with 2 divided by 2, which gives us an answer of 1. So, and the same thing here, 2 over 5, all right? So if we multiply 5 over 2 by 2 over 5, we will end up with 10 over 10, which will give us an answer of 1. So whenever you end up multiplying two reciprocal values, you will always get an answer of 1. So let's look at some examples here. 3 times 1/3. So the reciprocal of 3 is 1/3, just like the reciprocal of 2 was 1/2. It's 1 divided by the number that we are working with. So when you multiply it, you end up with a 1. Let's look at another one here. It's 3/5 times 5/3. So the reciprocal of 3/5 is 5/3. Like I said, when you take the reciprocal in a fraction of a fraction, the denominator becomes the numerator, and the numerator of the original fraction becomes the denominator in the reciprocal. And when you end up multiplying it, 3 times 5, 15, divided by 5 times 3, 15, gives us an answer of 1. And then finally, minus 6 times 1 divided by minus 6. All right, so when the reciprocal of negative 6 is 1 divided by negative 6. Again, the numerator and denominator flips, and when you multiply it, you end up with an answer of 1. Right? So now we are in the position of talking about division of fractions, now that we understand what reciprocals are. So it says to find the quotient. Quotient is the answer we get from a division, right? So to find the quotient of two fractions, multiply the first fraction by the reciprocal of the second fraction. All right, so let's look at how they work it out. Well, they have discussed this in general form, and the next slide we'll probably see an example. So if the first fraction is a divided by b divided by c over d, then the first fraction stays the same. All right, first fraction is a divided by b, but we flip the the second fraction, we flip the numerator and denominators of the second fraction, and we multiply it. So the division changes to multiplication, and we multiply by the reciprocal of c over d, which would be d over c, and then it ends up becoming a multiplication. All right, so ad over bc. So to divide two fractions, all you do is you change the division to a multiplication, and you take the reciprocal of the second fraction. All right, c over d becomes d over c. The first fraction doesn't change, it stays the same. All right, it's the second fraction that you take the reciprocal of and multiply it with the first fraction. But always keep in mind, in division we cannot have a 0 in the denominator. All right, we can have a 0 in the numerator, that's fine, but the denominator cannot be a 0. It'll end up giving us an undefined value. So neither b nor c can be a 0, and the d in the initial fraction, the second fraction, in the initial setup is what I meant to say, cannot be a 0 either. So none of these denominators can be a 0. All right? Let's look at some examples now of dividing fractions. The first example has 3/8 divided by 5 over 7. So again, remember the process in division. The 3/8, the first fraction will remain the same. All right, so I'm going to write here and I'm going to work up here, because when I pull up the results, it's going to write over, or it's going to show up over my writing. So let's write it here. It's 3/8, and then what happens in division? The division sign changes to a multiplication, right? So I'm going to write here multiplied, change the division to a multiplication, and we flip the second fraction, that means we take the reciprocal of the second fraction. So 5 over 7 will end up being 7 over 5. So 7 divided by 5. And now we go ahead with the multiplication. We work it out as we multiply any fractions. Multiply the numerators. 3 times 7, 21. Multiply the denominators. 8 times 5, 40. So the final result is 21 over 40. So let's see how they work this out. They have 3 times, okay, so they have 3 eighths. All right, 3 eighths is as is. And then they change the division to a multiplication, and they flip the numerator and denominator just as we did, 7 over 5 for a result of, okay, so something is wrong here, but let's just continue. All right. So we end up with 21 over 40 is whatever we got when we performed the division. All right, so let's look at a second example now. It's minus 2 over 9. All right, minus 2 over 9 divided by 3 over 13. Again, same process. The first fraction remains the same. So it's going to be minus 2 over 9. Nothing changes with the first fraction. The division changes to a multiplication, and we have to flip the numerator and denominator of the second fraction. In other words, we are taking the reciprocal of the second fraction. So 13 over 3. That becomes 13 over 3. So let's write that. 13 over 3 for an answer of negative 26. 2 times 13 is negative 26, and 9 times 3 is 27. So the final answer should be negative 26 over 27. Right? So let's go and see how they worked it out. So negative 2 times 13 divided by 9 times 3 is exactly what we did for an answer of negative 26 over 27. That matches with the answer we got, right? Now let's look into the two remaining operations, arithmetic operations that we can perform on fractions, and that's addition and subtraction. So to add or subtract two fractions with a common denominator, common meaning the same denominator, that means when the value of the denominators are the same in both the fractions, we add or subtract their numerators and retain the common denominator. So if we are in general terms, in algebraic terms, if the first fraction is a divided by c, and to it we want to add b divided by c. So here we see that the denominators are both c. That means they have the same value. Then all we do is write the denominator c, and we add the two values in the numerator. Again, provided c is not 0. Denominator can never be a 0. All right, keep that in mind. So we'll end up with a plus b divided by c. Now, if we were doing the subtraction, the same rule would apply. As long as a common denominators, as long as we have common denominators, same value in the denominators, we can just go ahead and subtract the values in the numerators. All right, so as show here, a divided by c minus b divided by c we write the common denominator once, and we subtract the two numerators. All right, so it becomes a minus b divided by c. So let's look at some examples now. All right. So we look at some numerical examples of addition and subtraction of fractions. So the first example is 1/8, 1 divided by 8 plus 3 divided by 8. So here we see that both fractions have a common denominator of 8. So that makes things easy for us when you work this out. And I'm going to work it up here. All right. So just give it a common denominator of 8. Whatever the common denominator is, write it just once, 8 in this case. You can just go ahead and add the two numerator values in this case. So 1 plus 3, all right, excuse me, 1 plus 3 gives us 1 plus 3 is 4, 4 over 8, but we can reduce this further. We learned how to reduce this. Divide both of them by the greatest common factor. So 4 and 8. 4 is the common factor for the numerator as well as denominator. If you divide, so let's see, 4 divided by 4 and 8 divided by 4, right? The comma divided by the same value, we will end up with 4 divided by 4 is a 1, 8 divided by 4 is a 2 for a final answer of 1/2. And we see over here, it's the results have already popped up. So they've taken the common denominator, written it once, they've added the two numerator values for a fraction of 4 over 8. Let's see if they have reduced it. Yeah, so they did reduce it to 1/2 by dividing both the numerator and denominator by the greatest common factor, which is 4. All right, so they got a result of 1/2. So let's see if they have an example on subtraction. So here we have 19 divided by 24 minus 5 divided by 24. So when the denominators are common, it makes things simpler for us. So we write the common denominator once and subtract the numerator values. 19 minus 5 for a value of 14 over 24, right? And now we can reduce 14 over 24 further for what is common between 14 and 24, common factor, 2. Right? 2 is the greatest common factor that will divide both 14 and 24 without leaving a remainder, correct? So it's 14 divided by 2 and 24 divided by 2. 14 divided by 2 is a 7. 24 divided by 2 is a 12. So the final answer should be 7 over 12. So let's see what answer they have come up with. So they did the same thing, 19 minus 5 over 24, and then which gave them 14 over 24. That's the same as what we got, and they should get 7 over 12 for the final result after reducing the fraction 14 over 24. They end up with 7 over 12, which is exactly what we got as well, right? We'll talk about the fundamental law of rational numbers and understand the concept of what's called equivalent fractions. Okay, so it says here if a, b, and c are integers with b not equal to 0 and c not equal to 0, and that immediately tells us, even though we don't see any fractions here, that b and c would be denominators, all right, because denominators cannot be a 0. So if a, b, and c are integers with b not equal to 0 and c not equal to 0, then a divided by b, if you multiply both the numerator and the denominator by the same value, then you will end up with an equivalent fraction. So it's going to be a times c, or ac divided by bc, and that is going to be what is called an equivalent fraction to the original fraction a divided by b. All right. What equivalent fractions means is that when we reduce, or the second fraction can be reduced back to get the original fraction, right? It's called equivalent fractions. It's not the same fractions, but it's called equivalent fractions. When we multiply the numerator and denominators by the same value, of course, the value in the numerator changes and the value in the denominator changes, but it can be reduced back to the original fraction, and therefore it's called an equivalent fraction, or it's called equivalent fractions, right? So now that we understand what equivalent fractions are, we can talk about adding or subtracting fractions with unlike denominators. That means when the denominators of the two fractions are not the same. All right. So when adding or subtracting two fractions with unlike denominators, first rewrite each fraction with a common denominator, then add or subtract the fraction. So what they're saying is when we have two fractions with uncommon or unlike denominators, then we first have to change them, make the two denominators common, all right, which we can do by creating equivalent fractions that we talked about in the previous slide. And then we can, once we have the common denominators, we can add or subtract the numerators, right? So we'll go through an example of that perhaps in the next slide. So let's look at an example here of performing a subtraction when the denominators are unlike. So we've been given two fractions, 13 divided by 15, and then the other fraction is 5 over 6, and we have to subtract it. Now we cannot just go ahead and start subtracting the numerators because the denominators are not common, they are different. So our job will be to first change the unlike denominators to a common denominator. Now, I will show you a process to get the common denominator, which may be a little bit different from the way the book has explained it, but I think the process that I use is consistent. It works for all cases, all right? So if you know that process, you can just apply it and get the common denominator quickly. So what I do normally is I take each of these denominators and factor them in prime numbers. All right, so let's do this here. 15. All right, 15, I will break it up into prime factors. The prime factors of 15 are 3 and 5, right? 3 times 5, and both 3 and 5 are prime numbers. And 6 has factors 2 times 3. Now I'm trying to get a common denominator, also called the least common denominator, or LCD. To create the least common denominator, what you do is take each unique value, each unique factor once, and then we'll multiply them. So 3 occurs twice, but in all these four different factors, 3 occurs twice, but you're going to pick it only once. So I'm going to write a 3, and then 2 occurs once, and then 5 is a unique factor. So 3 times 2 times 5 gives us a common denominator of 30. So 30 is going to be our common denominator. So once we get that, I'm going to put 30 as the common denominator for both the fractions. All right. Now that we have a common denominator, we have to, of course, make sure that the numerators are adjusted accordingly. All right. So we change the 15 to a 30. Right. So what did we have to multiply the 15 with to get a 30? 2, right? 15 times 2 is 30. So we essentially multiplied the 15 by 2. Now when you do that, you have to do the same thing to the numerator. So because when we change the denominator to the common denominator of 30, 15 had to be multiplied by 2, but you cannot just multiply the denominator by 2 and not touch the numerator. So both the numerator as well as the denominator have to be multiplied by 2 to make it an equivalent fraction to the original one. So 2 times 13 is 26. All right, so the first fraction, once we change the denominator, becomes not 13 by 30, but 26 by 30. All right, it becomes 26 by 30. Let's look at the second one. We changed the 6 to a 30, correct? What did we have to multiply 6 with to get a 30? 5, correct? So we multiplied the 6 by 5. You have to do the same thing to the numerator and to get 25 by 30. All right. And of course, now we have adjusted the numerator values according to the common denominator to make them equivalent to the original fractions. All right. And now that we have a common denominator, all you need to do is subtract the numerators and put it under the common denominator. 26 minus 25 should give us 1 over 30 as the final result. All right. So you'll see they have done the same thing here, but in a different series of steps. So let's pull that up. Just a second. 1 second. All right. So what they've done here is it's 13. They have taken the 13 over 15 and multiplied both numerator and denominator by 2. And they've done the same thing over here for the second one, but they've multiplied both numerator and denominator by 5. All right. And then in the next step, and it might write over or it might be pulled up over my writing. So I may have to erase this. So we have 26 over 30. So let me erase my writing here. So they got 26 over 30 and 25 over 30 was the same as what we got. And then they complete the subtraction process and get an answer of 1 over 30. All right. So let's just pull up the rest of it. 1 over 30 is the final answer. Now I'm going to put up a separate video on addition and subtraction of fractions with unlike denominators, and you can watch that and get an idea of how to go about it if you're not too conversant with it. All right.